I'll present the last talk for today. Hopefully, people are still awake, and we'll have a good good overview for electrical machines. A lot of very interesting subjects, and now to close up something a bit different, talking about linear actuators, and especially focusing in this presentation on the transient analysis, right, for linear actuators. So the outline, I'll briefly touch on the applications where we use linear motors and actuators, talk a bit about some considerations, what we need to take into account when modeling actuators, and then I'll go through an example, right? I'll take an example of a linear actuator, talk through the different setups, what we can model, look at some results, and then slightly add some more complexity, talk about the effect of hysteresis on these actuators, and finally looking at the system level modeling and comparing a bit the kind of results we can obtain from FEA directly and compared to what we can obtain when we do a system level modeling of this kind of device. So let's dive right into it. So linear actuators, basically just converting electrical energy into movement, but as different from electric motors, what we've been talking about for the past couple of hours, we're talking about linear motion. So there are many different applications, many different cases where we want to have a linear motion. We want to actuate something in the linear direction. Obviously, industry, there are many, many different examples in that case. So positioning systems, positioning arms. In the transportation, so things like, for example, maglebs. So it's a linear system for propulsion. We're talking there more about a linear motor than an actuator, but the physics, the principles are very, very similar. A lot of the equipment used to build, for example, electronic components like semiconductors, a lot of them require very, very precise movements, and really this can only be achieved, or it's best achieved, let's say, with linear actuation. And obviously many different household appliances as well contain many numerous motors, linear motors or linear actuators inside. And yeah, also a bit of a niche application, but I quite like it. You know, it fits into the green energy, various different projects out there for capturing the energy from waves, so tidal energy, and some of them do use linear actuation, so positioning vertically under the water to capture that energy. So why linear actuators? So what are the benefits, right, of converting directly this electric energy into linear motion? So first of all, we could use let's say a normal type of motor, rotating motor, to convert the electrical energy into rotating motion, and then use a system of gears to and other mechanical components to convert that into a linear motion. Obviously, all of that adds complexity, reduces the efficiency of the conversion, and this is where linear actuators, they go straight from the electrical energy to the type of motion we need. So obviously the energy efficiency is much higher. Obviously, removing any other mechanical or as many mechanical components as possible, that also reduces the mechanical losses and any other energy, any other electrical losses used by maybe a rotating motor. It also gives us better control over, well, the position that we want to achieve, but also the force that we want to generate and the speed acceleration at which we want to move the actuator or the linear motor. And a lot of the times, obviously, we are also reducing the complexity of the control strategy, which means using less components, electronic components in our inverter, and a simpler method for controlling these devices. When modeling these devices, so obviously electromagnetic tools, low-frequency electromagnetic tools are what we would use for simulating capturing these kind of behaviors. But there are some specificalities, specific things that we need to keep in mind, or we need to be able to include when modeling linear actuators. So a few of them, by no means it's not an extensive list, but some of the important things which also I will be touching on during this presentation. Being able to model the accurate motion by defining maybe rigid body dynamic equation, where we can incorporate any friction, any loads, any other maybe viscous friction coefficients into the simulation, into the finite element simulation. Also, because we're talking about moving components, sometimes we do have induced currents, maybe, so motion induced effects. These also have to be captured and accounted for. Co-simulation, so a lot, or the majority of these kind of devices, as I said, we are talking about the control strategy, we are talking about the electric circuit which drives the current, and there is often a very close relationship between the control strategy, the position at which we are, maybe limits on the currents and things like that. So we have to co-simulate the electromagnetic analysis and the circuit at the same time. And finally, what I will also cover is looking at the importance of having a accurate and fully defined material model. So there are obviously things like magnetic nonlinearity that needs to be included, but also effects that depend very much on the type of, let's say, steel maybe that is used. So hysteresis, the effect of because the moving part, right, it's moving constantly between different positions, it can accumulate in time a remanent field on there, which will change the behavior of the actuator in time. So let's try to go through all of these considerations by looking at one particular device. We'll take one example, look at component parts, what we need to set up, and results for this example. So if we take the example of a linear actuator, a tubular linear actuator, we can see here a cross section of this actuator. Fairly simple, right? Moving between two different positions. On the right-hand side on the graph, let me bring up the pointer. So on the right-hand side here, we'll assume this is, let's say, the open position. So when the shaft, when the shaft of the plunger is at the right most side of the motion, and then when it reaches the end of the motion on the left-hand side, we'll consider that, let's say, the closed position of this particular actuator. So looking at the components very briefly, we have the static part, which is highlighted here, which is made up of steel. In this case, we took a material characteristic from our database, 10-8 steel. And we have a permanent magnet in pink here on the right-hand side, oriented as this arrow indicates, so from left to right, a certain grade of permanent magnet material. So this is the stationary part of our plunger, of our actuator, pardon. And then the moving part or plunger, as it's also called. So using the same type of material, still 10-8. And you'll notice we also have another permanent magnet at this end of our plunger, also oriented in the same direction as the one on the stationary part. And obviously the intention here is that when we are not putting any current in the coil, we'll see in a second, the control part, our actuator will stay in the open position. So these two magnets will attract. So the moving part will want to move to the right hand side of the screen here. Now I talked about material properties. So obviously, besides the accurate representation of the geometry, capturing the having a good mesh discretization, the other very important part is having a accurate representation of the material properties in whatever this device, in this case in the actuator. So we are running a nonlinear simulation. So saturation is usually quite significant with this type of devices. So it's important to have a BH curve for our steel. We're also using a non-linear characteristic for our magnet. And you can see here on the right hand side the BH characteristic for the permanent magnets, for the N50H permanent magnets that we use. So these are the main components in terms of the steel and the permanent magnets. And the third component is the coil. So this is what will create a magnetic field, and we'll see what effect this current in the coil will have on the motion of the actuator itself. The coil is connected to a circuit, to an electric circuit. Very simple in this case. We try to keep it simple for this example. We have a in this circuit we have the representation of the coil, which is, if you like, the connection between our finite element model and the electric circuit. So as I said, we are doing a co-simulation between the two, and this is, if you like, the link between our 3D finite element model and the circuit equations. So looking at the circuit itself, four main components. We've talked about the coil. It has a certain resistance which we put in series with this coil. It has 400 turns, and this is basically what represents the parameters for our coil. The other two components are a DC voltage source. So this DC voltage source at 48 volts, and we have a switch here in series with our voltage source and the winding, obviously. We've defined a switching function, or a switching function for our switch based on the time. So we define the period of motion, and the switch will be closed and open depending on where we are in that simulation. Now the next part is defining the type of motion that we want. Again, there are different ways in which we can define the motion. We wanted for this example to make it as realistic as possible and define what we call the mechanically coupled equation of the moving part, where the electromagnetic force is calculated at every time step during our analysis. Obviously, we define the mass, and the acceleration is calculated by the software from the force. Now, in the force itself, so for this particular actuator, we calculated based on the volume and density of the material. So we have a mass, but also the force itself, as I said, is made up of the electromagnetic force, but we can also include things like friction, which will always oppose the direction of the movement, any other loads that our plunger might be connected to, it might be actuating something, so there is a force there. And this also can be functional, so it can be a force as a function of position, or a load as a function of position. So we can model in that way a spring, as the plunger is getting towards the end position. So this is the kind of motion that we have defined for this particular example. Now let's have a look at first of all the drive cycle. So as I said, we have our electric circuit, and we have here a view of the actual current through the coil. So what we're doing is we start the simulation with no current, so the switch is open, and at 1 in minus 2 seconds we are closing this switch. So you can see here at the beginning of the plot we are closing the switch. So as we'd expect, the current rises in the winding, and at a certain point at 0.15 seconds we are opening the switch again, right? So this is our cycle, closing it here, opening it here, and then we let the current to decay, or we keep the switch open. We allow it to decay for 0.4 seconds. That's our cycle. And then we repeat this cycle one more time, the exact same cycle, leave it for another 0.01 seconds, switch it on, and then switch it off at this point. And we'll see why we're doing it for 2 cycles instead of 1. But as you can notice already a few characteristics with this current. So as you'd expect, the current starts to rise. Then we have this dip here, and then it reaches pretty much, the peak value. As we said, we have a 48 volts DC source. We have a resistance which represents the resistance of our winding of 2 ohms. So you'd expect the DC current, let's say, when it reaches the DC value, is 24 amps. And this is what we see here. Now let's look a bit at what is actually happening here. Why is that happening? And for this, let's have a look at the motion. The motion characteristic, again, the output from our analysis. So we started the position somewhere around here, if you can see my cursor. And as we haven't switched on the current yet, the current in the coil is 0. So those 2 magnets, if you remember, they're pointing in the same direction. So the tendency will be for the moving part to move to the right, which is, for us, it's the negative moving direction, so the negative W axis. And this is the limit of our motion, right? So the plunger stops at that point. It cannot go any further. And from here, then it starts to go into the other direction, all the way up to here when it reaches the end of its movement. Then it stays there while we have the peak current in our winding, and then it starts moving back up and stays at the end position again until we go into the next cycle and we switch again the current in the coil, and we redo the cycle once again. And you can probably have an idea already, right? So I mentioned on this graph we have this dip here. So as the moving part is reaching this end here, the current drops for a few instance of the motion until it recovers and starts to go up again. This is due to the inductance of the system. And we can also look at the force, which again, tells us the same kind of story. We start with a negative Z force. So as I mentioned here, we'll assume the positive direction to be right to left. So in this direction, if you can see the axis. So a negative force bringing those 2 magnets together up until this point where the current is starting to increase. We're crossing 0 force. So now the force, the electromagnetic force from the coil and the force from the magnet are equal. And from this point onwards, the force from the electromagnets has it's larger than the force of the magnet. So the moving part is now moving away from the magnet and going at the other end while it stays there, is stabilized. And then we switch off the current, force drops to 0, and as the moving part moves back closer to the magnet, this force again drops, and we have one more cycle of that. And you can see here the same view with the position. Now, let's introduce into the equation hysteresis. So what is magnetic hysteresis for those of you who maybe are not that familiar? So all magnetic materials retain some magnetization after they have been exposed to an external magnetic field. So this means if we have a piece of steel, we expose it to some external magnetic field, obviously you will have some field distribution, maybe even might get saturated. But once we remove that external field, the material itself does retain some magnetization. Usually it's very small. It can be negligible and it can be ignored in a lot of simulation. But depending on the type of material, depending on how big this hysteresis is, there are some effects which need to be taken into consideration. So things like losses. So there are hysteresis losses which will generate heating, but also the actual behavior of the device can change depending on the size of this hysteresis behavior, how big of a difference this hysteresis makes. Now, and as I said, some steels, depending on their characteristic, might have a very narrow hysteresis band, a very narrow curve there, and can be, in most cases, approximated to an unhysteresis curve, which is this red line, which we normally use, and I was using in the previous, originally in the example. But some materials have pretty significant hysteresis, so this blue line, and this means that we need to include that effect in our simulation. So our solvers allow for the full definition of hysteretic materials. We employ a proprietary method using trajectory following method scheme. It has quite a few benefits. Obviously, accuracy is most important, so we want to make sure it's very, very accurately capturing these effects. But the method also requires, compared to other methods, a reduced number of points. So basically, we only need to define a quarter of this full blue line. So from the first quadrant going all the way into saturation, and then the software will calculate the internal, the minor hysteresis loops. It's also very memory efficient because it doesn't need to maintain the full history in mind, but just the previous step. And obviously it allows us to calculate the loss, which is, as I said, quite important, can make a big difference when it comes to the efficiency, but also thermal analysis of the device. And crucially, at least for this type of application, it's something that is being calculated during the solving stage. So we do have the effects of hysteresis not just as a loss at the end of the analysis, but actually having an effect on the behavior of our device. So very briefly, really just specifying, instead of our normal nonlinear characteristic, we specify a hysteretic curve. As I said, just the outer shape of that hysteretic BH curve needs to be specified. So this is what I've used for this particular example. Now, let's have a look at a couple of the results. So I didn't show in the initial case, but the magnetic flux density, obviously, as I said in the first presentation, simulation gives you the option of visualizing the fields, what happens inside your device. So we can see here we've got a B field of almost up to 1 Tesla in the parts of the plunger, where we'll have the coil there around, but also at this end where the magnet is and the interface between the magnet and the steel. But more interesting in this case, we can have a visual representation of the hysteretic losses. So we can see how these losses are distributed at every time step of our analysis across the entire device. So then we can get an idea of where maybe we need to use more material, or we need to reshape that component. Now, let's have a look actually at the characteristic. So what's happening when we employ a hysteresis material? And this is, quite interesting. We have in black our original characteristic for the motion, and in red we have the characteristic when we're employing a hysteretic material. And what we can see here is that for the first part of our cycle, those two are fairly identical. So the moving part is going all the way to the right-hand side. It's touching the magnet and then starting to move in the other direction. But what we see is that once we reduce the current, right, at this point we are opening the switch, the plunger doesn't move anymore. So the plunger is stuck in this end position, right? And even if we switch off the current completely and we switch it back on, the plunger is stuck at that position. So this is what's called the latching, and it's quite an extreme case. Usually, obviously, this is not something you want to have in operation. So in this case, you might need to redesign your plunger or your coil. And we can also see the effects if we look at the force, right? So the force in red, we see that it doesn't actually get to such a low value as in the case with a normal BH curve, but this is to do with the energy that is stored in the system. And actually you can see even once we switch off the current completely, the force never goes below zero. So we don't get a negative force, so the plunger doesn't start moving back towards the start position. You can maybe see a very slight difference here while the current is switched off. So there is a decay in the force, but it's very, very slow. As I said, this is the latching force, which keeps our plunger stuck at one end. And we can see also very nice behavior in the current, because our, if you like, our device has that stored energy. We don't get this dip anymore in the current when we do it, when we go into the second cycle, when we redo this applying of the current in the second cycle. So definitely, being aware of the hysteretic behavior of your material is very important, because it can have a sometimes detrimental effect to the behavior, to the application, and you might not know why is my plunger not moving back when I'm applying the same kind of current. And lastly, let's have a look at how do we take this information of the characterization of the linear actuator, and we plug it into a system level model, which then can include many more components to which the actuator is linked to, connected to. So I won't go again into these details. We discussed them. So the system itself, the device itself, the actuator doesn't live by itself. It's usually there to control something. It's connected to something. So there may be many other interactions. Also, there may be many other considerations to include from the inverter side, some more complex switching that happens in the inverter. And in that case, we might want to look at the full system level behavior of the entire system, including the actuator. So we can do this characterization. So the first thing is to perform a characterization from a series of static analysis of our actuator, from which we can then extract the reduced order model, which in this case is a map of the flux linkage of our actuator versus the position, so for different positions. And then using a system simulator like Dymola, we can describe an entire system level where we have the representation of our linear actuator as this lookup table of the flux versus position. We have the sensors for the position, we have the sensor for the current, the force that is calculated. We can add additional forces, we can add loads, springs, and any other mechanical components, and simulate the entire system. And once we have this reduced order model of the actuator, running this system level simulation takes a second. It's almost instantaneous. So it allows you to very quickly and easily do what-if scenarios, connect other loads, and look at the full system-level view. And when we compare the results, so we have on the left-hand side the results from the system-level simulation from Daimola, and on the right-hand side the full 3D FE simulation that we were looking at. You can see we get very very good agreement between the two. So if we look at the position, and also if we look at the forces, if we look at the current, we see the same kind of profile, same kind of peak values, and even this dip, which is due to the inductance of our actuator. So that is the linear actuators transient simulation presentation I want to talk to you about. So very quickly, as a summary, actuators are everywhere in the industry. Being able to simulate them requires being able to include and to capture quite advanced material models and circuit simulation coupling. Plus, we need to have this motion component, which is crucial for having a dynamic characteristic of the actuators. And with our electromagnetic tools, SIMULIA Electromagnetic, CST, and Opera, we provide all of the capabilities needed to accurately capture and represent these type of actuators. And finally, we can also take it one step further and link all of that into a system-level modeling using, for example, Daimola. Okay, and that is the end of my presentation.